Don's Manufactory. Well, I'm just doing some odd tasks here. Finally got this dang tachometer finished up, I think. See, you can tell how much confidence I have in that. I've had it together and apart many times with a bunch of different calibrations. Hi, welcome to Don's Manufactory. Well, I'm kind of waiting for Bondo to set up, so I thought I'd do something fun. So this car hasn't ran for, I don't know, a year and a half. So the first thing I did was I just put gas in it so that I can fill the vent tube. So the easy way to start these when they're dry is to pour gas into these vent tubes, bring the fuel level up so the carburetor is full. And then you don't have to wait for fuel to get there from the tank. It'll just sit there and idle. And hopefully fuel will get there before the carburetor's empty. And if that doesn't happen, I just fill the carburetor again, start it right up. In the meantime, I rigged a gallon can here. And yes, there's a little tiny hole over here to vent the can so the fuel will actually go out. I had to do some wire fix up. The coil power wire here and the harness up in there. I kind of had to fix that stuff. Poured coolant in it. I'll have to be double checking that after it runs a little bit. And I filled the recovery tank too. Okay. Let's see if she goes. Here we go. Let's see how my setup is. Okay. Everything seems copacetic here. Pull the choke on, pat the gas pedal. Starts right up. There's the tach working like it should. Yeah. I have the tachometer torn apart again. And I did this for a couple of reasons. The first, most important reason was after I changed this capacitor to correct its reading, it's accurate now. However, it's also sluggish. So the meter doesn't keep up with the motor. If you blip the throttle, the needle just barely wants to move. But if you hold it at any given RPM, it goes right to that RPM and reads accurately. So what has happened here, I believe, is that I've screwed up the time constant that I spoke of in the last video. There needs to be a schematic. I could not find one online, so I decided to create one. Here's the schematic. First thing of note here is this device here is unknown. I tested this. I couldn't get it to read capacitance. I couldn't get it to read inductance. Resistance was dead short. I don't know what it is. So, hey, if you out there in the video world, in YouTube land, knows what that device is right there. It makes sense in the circuit that it would be a capacitor. Well, in this case, it's trimming off the higher RPMs off the tach. So when setting it up, go for the lower RPMs, 2000, get 2000 accurate and 1000 accurate, and then if it starts reading high or low in the upper frequencies, then you would adjust this resistor to add or subtract the higher RPMs. In mine, on my tachometer, this resistor here read, well, it was all over the place. When I first tested it, it was 1.4 kilo ohms. It's marked with the rings to be 820 ohms. Every time I got the solder gun near it, it changed its reading. So I had to replace this resistor for sure. Okay, let's analyze this circuit and see what happens here. When the coil pulls current, so the points close, the coil is pulling current, that's pulling current through the primary of this transformer. So it's going to put out a pulse on the secondary side of this transformer. There's a big pulse going up as the points close, and there's a big inrush of current going into the coil. Then as the coil begins to saturate, so this will kind of go up and go around, but as the coil begins to saturate, current starts to trail off. Eventually the points open and there's no more current flowing into the coil. At that point, the secondary fires. There's oscillations that are bouncing back and forth between the points, between the coil, causes flyback voltage, which goes negative. So then the waveform kind of does something weird like this and then goes back to normal. So now that you know what the waveform looks like, let's look at the circuit. It comes out of the secondary transformer and is limited current-wise by this 15K resistor. After that, there's this shunt. It's an 8.2 volt shunt. It's kind of the forerunner to a Zener diode, but it's a A6441 shunt. That's just what it's listed as. Totally obsolete part, can't get those. But you can just substitute a Zener in there. So they're taking this waveform right here and saying, okay, we're going to go up 8.2 volts and just clip the top of that waveform off. Okay, so now we've got to deal with all this negative stuff. And what they chose to do when this waveform is positive, it's pushing current limited by the 8.2 volts through this diode and through the meter, and then it begins charging up these caps, these capacitors here. And it will continue to pull current through the meter until this capacitor is full. And then it'll stop. When the waveform goes negative, it can't do anything negative this way because this diode won't allow it. So when it pulls negative, current flows the opposite direction through this diode, which shunts everything to zero, and the negative waveform just helps discharge these capacitors to zero. So every time this circuit goes through a cycle, it gets a positive pulse through the meter, and all the negative stuff is trimmed off to zero, and the capacitors go back to zero. So you get a nice waveform, which is just a positive waveform cut off at the zero line. So we're also trimming off all of this. So essentially the waveform looks like, comes up, does that, comes over, comes down, and there you go. That's it. And it's got an 8.2 volts. So this has to be enough current to charge the capacitor to 100%. And it cannot exceed 50% of the duty cycle at the rated RPM. So at 6,000 RPM on my tach, or 8,000 on yours, whatever, this pulse here cannot exceed 50% of the time because it needs to charge to 100% and discharge to zero every cycle. Okay? And that is how this circuit works. It is just a charge pump, pumping current through this, charging these capacitors. Then the circuit goes negative, capacitors discharge to zero, and no current flows through the meter. It's shunted to zero, so there's no current trying to pull the needle back down. The time constant can't be too fast because the needle on the meter would flutter. But it can't be too slow, or you end up with the problem that my tach had, which is the meter becomes really sluggish. It reads accurately, but it doesn't keep up with the motor. The motor can rev faster than the meter can move. Okay, so that becomes the problem of the circuit. Now, if we look at this here formula, I is the current in amps that goes through the meter, so that's how much current goes through the meter and charges these capacitors. Frequency in cycles per second, capacitance in farads, that's not microfarads, that's farads, and E equals the voltage. So if you look at this, we are creating a constant out of the voltage by means of this Zener diode. We have a constant of the capacitance because these are not changing value. So if that's a constant and that's a constant, then the current through the meter becomes directly related to, or directly proportional to, the frequency of the pulses, which is the RPM of the motor. This whole design, I have to say, is kind of a ripoff of a Thomas Faria design from 1958. And this would be very Ford-like, to change things enough that they wouldn't have to pay for the patent. So what has changed from the Faria design is this filter network here, which I believe was not necessary in his design because Faria used a neon bulb here as the voltage limiter. I'm going to write the guy's name here so you have it. Thomas G. Faria, 1958. He's the guy that had the patent on this design tach. And that's the theory that it runs under. And it's accurate as all get out because, I mean, mathematically, this doesn't vary. The only variables we get are inside the meter itself, whether its readings are linear, which are dictated by the way the magnet is set up, the way the Gauss around the field is set up, and how the springs are rated. So if the springs are perfect and the meter is built perfect, and then it should read perfectly, but that's never the case. So they become sort of an average, and that's true for just about all the tachs. You can build the electronics part of the tachometer as accurate as you want, but the analog meter readout becomes the variable that makes it inaccurate. So hence, if you have a digital readout, hey, then you don't have to worry about that. In my tachometer, you can see that I replaced, I tried originally to change this capacitor, but I slowed down the time constant, which went beyond 50%, and then the tach didn't work properly. So I ended up having to take it all apart again, reduce the capacitance, and what I chose to do was increase the voltage instead. So I can have a lesser capacitance with a higher voltage, and it will charge and discharge faster and not affect the performance of the tach. I had to get rid of this variable resistor here, so 1K, half-watt resistor in this position. And here, in this scene right here, you can see I'm just taking a Zener diode of a different voltage. That tachometer only had a 0.1 microfarad cap in it with a 9.1 Zener. So to change that to an 8-cylinder, I went from the 9.1 down to an 8.2. On mine, I decided because my magnet has gotten weak, was actually marked, and you can see it right here, it had a 325 on a piece of masking tape right on the side of the meter. 3.25 milliamps at full scale. But it now requires 3.52 milliamps to get to full scale. And that is because the magnet has gotten weaker over time. Now, I'm not taking it apart and regaussing that magnet. That would just be, could it be done? Absolutely. Would I want to do that? Absolutely not. It sounds like I wouldn't be able to get the meter back together and make it work right. I tell you, when I was working on my tach, here, in these shots right here, you can see the spring was fatigued on my meter. And so I think maybe between taking it apart and putting it together a bunch of times and having the wires bind up against it, ended up breaking the spring off of the rear of the movement. So I did have to disassemble my meter, take the rear bearing off, reattach the spring to the center windings, then reassemble it, glue it back together, and reattach the spring to the adjustable arm on the rear movement. And it was excruciatingly tedious, but I managed to fix my own tach movement. And I don't wish that on anyone. I didn't document it real good because I was in full-on freak-out panic mode because I thought I had ruined my tach and I was going to be out the $300 for a new one. Basically, over the years, I've replaced this diode from the 2069 to a 4005. It's got a 600 volt rating. That diode should never pop again. I had to up this voltage, and one of the things I wanted to do was, it had two big capacitors like this inside that tach, which took up a lot of room and blocked the light to the display. I used two of these, and you can see how the difference is. This is still a 250 volt cap, so it well exceeds anything that's going to happen inside the circuit. Look at how small it is. So I used two of these. And why two? Well, because it actually allowed me to adjust a bit. I got two of the lowest value capacitors I could find, and when I put them together, I ended up with 1.995 microfarads. That is how I fixed my tachometer. And so now what I'm going to do is, let me just run through the math real quick so that you can do this too. 400 times 0.123456 times voltage. We'll just make it 10 volts times 4, 3.2 milliamps, 3.25. So I think that's how they figured this out. 400 pulses per second times my capacitance, 0.123456622. That's the capacitor I put in there. Times 10 volts times 4. 3.52 milliamps. So that's what it takes to get to full scale on my meter now. So that's why the 0.2, why I need the 2.2 here instead of just 0.2. I just couldn't do that because it made the whole circuit too slow. So what I did instead was, next calculation, 400 pulses per second times the capacitance is back to 0.123456 times 11 volts times 4. And so, by putting the capacitance back down to 0.2 and upping the voltage from the 8.2 to a 9.1 Zener, so basically going up a volt there, what I ended up with is the exact 3.52 milliamps I needed to drive my meter to full scale. That was the calculation. It worked. Okay, so something has come up. One of my viewers has a dead tach What he had done was, see, they used red and black wires coming out of this transformer on the primary side. So I believe what he thought was he was supposed to hook one to power and one to ground. And so he had full current coming from the ignition switch going through this primary winding. So these wires are fairly large in diameter, and they are running in parallel. So that is an incredibly high current winding. So he says his tach doesn't work, and I have to get more information from him, because if the motor still runs but his tach doesn't, that means that when he shorted this, the amount of current and signal going through this diode exceeded its capability. And so it blew this diode out right here, and so the tach doesn't work. What might have happened, if he plugs it in and the motor doesn't run, then that means he burned up his primary windings. But if the motor does run, that means this part of the circuit works, and what he really did was took out some of these diodes here. May have exceeded the voltage and current rating on the on this Zener. Could have popped that, but it for sure is going to pop the one of these diodes, or both, or all three. I don't know. That's my diagnosis for his problem. So Whamabama, if you're watching, that's probably what happened. Well, I was really hoping that we'd come up with a solution for Whamabama's tach problem, but at the time of this video, still no solution. I have had more communication with him about his problem, and I'm just hoping we can get it fixed. That would be really great. I know this video was pretty heady, as it were, technical, whatever, but I just felt like, because of the lack of information about these tachs out on the internet, or just in general, I just decided there needed to be a record of how they work, how to fix them. Here's the drawings, you know, everything that I could ascertain. Anyway, it'll maybe do somebody some good in the future. I don't know. Anyway, so that's about it for this video. I thought I'd give you a little look around. You can see just how clean everything is getting. I am slowly converting my garage into a paint booth, which includes this nice nifty little screen door that I made right here. See, it's just got some magnet catches and seals and a threshold that goes under the door there so my hoses can go out into my bucket. And I have filter material to go in this, as you can see right here. Here's the filter material I got. It's about 3/4 of an inch thick or so. Not ultra thick. It's got the tacky spray on it for collecting dust. So I think I'll probably have 3 layers of this in the door. So slowly I'm getting it cleaned up. The walls used to be 3 feet thick, but now they're not. I'll put tarps up to turn the walls white and protected, and tape everything off, the ceiling and the door, and clean everything. And then I can start painting. We're going to have another week, possibly 2, of good weather. I can have the door open, fans running full blast, and I'll have warm air coming in. That'll be good. That will wrap it up for this here video. Thanks for watching, and I'll catch you later.